Good morning. I'm Dhanalakshmi and welcome to this session of Chapter 3 Matrices of Plus 2 Mathematics. The topics that we are going to discuss in today's session are transpose of a matrix, properties of transpose of a matrix, symmetric matrix, skew symmetric matrix, and some results related to symmetric and skew symmetric matrices. First, let me explain what the meaning of the transpose of the matrix. First, let me take an example, matrix A of order 3 by 2. 2, 3, 4, 5, 6, 7. Let me rearrange this matrix and write it as 2, 4, 6, 3, 5, 7. What are the changes seen in this new matrix? We can see that the first column of the matrix A has now become the first row of this matrix, and the second column of matrix A has become second row. In short, I can say the first row becomes first column, the second row 4, 5 becomes second column, the third row 6, 7 becomes third column. This process of interchanging the rows and columns of a matrix is called as the transpose of the matrix and is denoted by A dash or A raised to capital T. Never read it as A raised to capital T, we should always read it as A transpose. Also note that the entry A1, 2, the first row, second column 3, in this matrix it comes in the position of A2, 1. Similarly, A3, 1 element, third row, first column 6, comes in first row, third column. In short, what can I say? In the transpose of the matrix, the entry Aij becomes Aji. Also note that if the matrix is of order 3 by 2, then the order of the transpose is 2 by 3. So based on this example, we can define the transpose of the matrix as the matrix obtained by interchanging the rows and columns of matrix A is called as the transpose of the matrix A and is denoted by A dash or A raised to capital T. If A is of order m by n, then the transpose A dash is of order n by m. Now we'll see to our problem. What is the transpose of A is equal to the matrix 1, 2, 3? The speciality of this matrix is it's a row matrix. So the row matrix is of order 1 by 3. So when we take the transpose, you can see that A transpose is equal to the matrix 1, 2, 3. The row matrix becomes the column matrix. The order of the matrix A is 1 by 3 and the order of the matrix A transpose is 3 by 1. Next, we'll see to the properties of the transpose of the matrix. For any matrices A and B of suitable orders, we have the first property, the transpose of A transpose is equal to A. It is almost related to the theory which you had studied in the plus 1. Under set theory, A complement is equal to A. Similarly, the transpose of A transpose is equal to A. Second property, K into A the whole transpose can be written as K into A transpose, where K is any scalar. So when the transpose is taken, the scalar can be kept outside and the transpose of A alone can be written. Property 3 says A plus B the whole transpose is equal to A transpose plus B transpose. The bracket can be expanded. Property 4, A minus B the whole transpose can be written as A transpose minus B transpose. And the last property of the transpose is AB the whole transpose, which is equal to B transpose A transpose. It is called as reversal law because the matrix is taken in the reverse order. AB the whole transpose is B transpose and into A transpose. The properties are used to prove some of the results in this and also for the problems. Next, we'll talk about symmetric and skew symmetric matrices. Consider the matrix A is equal to, it's a 3 by 3 matrix, 1, 4, 5, second row 4, 2, 6, third row 5, 6, 3. When I find A transpose, you know that the first row becomes first column, second row becomes second column, third row becomes third column. So we get A is equal to A transpose. So such a matrix where A transpose is equal to A, it is called as symmetric matrix. Also you can note that in this A12 is same as A21, A13 is same as A31. In short, I can say Aij is equal to Aji. Also, we can see that the symmetric word is very familiar for you because you studied under conic section in +1 topic. Like when we say y squared equal to x, it is symmetric about x axis. In the same way, here, when you see the main diagonal 1, 2, 3, the entries above the main diagonal and below the main diagonal are same. You can see that 1, 2, 3, 4 is coming here, here also 4, 5 in this position, here also it should be 5, 6, 6. So the entries are same above and below the main diagonal. So this matrix is called as the symmetric matrix. So based on this, we can define the symmetric matrix as, since we talk about the diagonal, it should be strictly a square matrix. A symmetric matrix should be strictly a square matrix. So a square matrix A is said to be symmetric matrix if A transpose is equal to A. That is, Aij is equal to Aji for all I and j. Now we'll do a problem under symmetric matrix. Show that the matrix A is equal to 2, 3, 3, 4 is a symmetric matrix. So whenever you want to show any matrix is a symmetric matrix, as per the definition, we have to show A transpose is equal to A. So first we have to find A transpose. So taking the A transpose, you get the first row 2, 3 becomes first column, second row 3, 4 becomes second column, and you get back A itself. So since you have proved A dash is equal to A, we say that A is a symmetric matrix. Next, we'll discuss about skew symmetric matrix. Let me take an example to explain the skew symmetric matrix. Let A is equal to the matrix 0, 2, 3, minus 2, 0, minus 4, minus 3, 4, 0. You can see the entries above and below the main diagonal are almost same except for the sign. So we cannot call it a symmetric. It is something connected with the symmetric property. So let us see. When I take the transpose of this matrix, I get A transpose is equal to first row will become first column, second row becomes second column, and third row becomes third column. Now we'll take the minus sign out. What happens? 0, 2, 3, 2, minus 2, 0, minus 4, minus 3, 4, 0. Now you are getting back A. Therefore, we can define the skew symmetric matrix as A transpose is equal to minus A. Moreover, you can see that A12 is 2 here, but A21 is minus 2. A13 is 3 here, A31 is minus 3. In short, I can say that Aij is equal to minus Aji. So, based on this problem, we can define the skew symmetric matrix as a square matrix is said to be skew symmetric if A transpose is equal to A. Also, Aji is equal to minus Aij. You can see that the diagonal elements of the skew symmetric matrix are 0. I'll give a small explanation for this. When I say diagonal elements, it is A11, A22, A33. Why all those entries are 0? Because as per the definition of skew symmetric matrix, Aij is equal to minus Aji. So, for diagonal elements, we know that I is equal to j. So, when I give I equal to j in this, Aii becomes minus Ai. So, bringing it to this side, we get 2Aii is equal to 0, which means Aii is equal to 0. And that means A11, A22, A33 is equal to 0. Therefore, we can conclude that the diagonal elements of skew symmetric matrix should be zeros. We will do a problem under this. Show that the matrix A is equal to 0, 2, minus 2, 0 is a skew symmetric matrix. As the theory goes, whenever we want to show any matrix is a skew symmetric matrix, we have to show A transpose is equal to minus A. So, the first step which you have to do is take the transpose of the given matrix. So, A transpose is equal to the first row becomes first column 0, 2, second row minus 2, 0 becomes second column. Now, taking the minus sign out, we get 0, 2, minus 2, 0. Now, we are getting back A. So, that is equal to minus A. Hence, we can conclude that if a matrix is a skew symmetric matrix, A transpose should be equal to minus A. Next, we will prove a theorem for any square matrix A plus A transpose is symmetric and A minus A transpose is skew symmetric. First, let me take an example to prove this. Let A is equal to the matrix 1, 5, 6, 7. Then A transpose is equal to the first row will become first column 1, 5. The second row becomes second column. Now we have to prove A plus A transpose is symmetric. So first we will find A plus A transpose. Adding these two matrices, we get 1 plus 1 is equal to 2, 6 plus 5 is equal to 11, 6 plus 5 11, 7 plus 7 14. And you can see that the entries above and below the main diagonals are same. Therefore, this is a symmetric matrix, since when you take the transpose A plus A transpose, the whole transpose, you get back the same, which means A plus A transpose is a symmetric matrix. Now we have to prove A minus A transpose is skew symmetric. Find out A minus A transpose. What do we get? 1 minus 1, 0. 5 minus 6, minus 1. 6 minus 5, 1. 7 minus 7, 0. At a glance, you can see that the main diagonal entries are 0 and the elements above the main diagonal and below the diagonal differ by a sign. So, in order to show that this is skew symmetric, we have to take its transpose. Therefore, A minus A transpose, the whole transpose will be equal to, the first row it becomes 0 minus 1, the second row becomes second column. Now when you take the minus sign out, we get 0 minus 1, 1, 0. That is equal to minus of A minus A transpose. Therefore, we have shown here A minus A transpose, the whole transpose is equal to minus of A minus A transpose. Therefore, A minus A transpose is skew symmetric. Next, we will prove this theorem for A to be any square matrix. Using the properties of transpose, for any square matrix A with real entries, we have to prove A plus A transpose is symmetric and A minus A transpose is skew symmetric. Whenever you want to prove any matrix is symmetric, you have to show its transpose is equal to the matrix itself. So, A plus A transpose, the whole transpose, by the property of the transpose, A plus B, the whole transpose, can be written as A transpose plus B transpose. Therefore, A transpose plus A transpose, the whole transpose, which is nothing but A transpose plus A transpose, the whole transpose, by property 1 of the transpose, it's A. Since matrix addition is commutative, A transpose plus A can be written as A plus A transpose. So, you have proved that A plus A transpose, the whole transpose, is equal to A plus A transpose itself, which means A plus A transpose is symmetric. Now, we have to prove that A minus A transpose is skew symmetric. Again, we will go for its transpose. So, A minus A transpose, the whole transpose, can be written as, by the property of the transpose, A minus B, the whole transpose, can be written as A transpose minus B transpose. Therefore, this is equal to A transpose minus A transpose, the whole transpose, which is nothing but A transpose minus A. We will take the minus sign out so that when minus comes out, we get it as A minus A transpose. You get back the same. Therefore, you have proved A minus A transpose, the whole transpose, is equal to minus of A minus A transpose, which implies that A minus A transpose is skew symmetric. We will use this theorem for the next theorem, stating that every square matrix can be expressed as a sum of symmetric and skew symmetric matrix. Just now we proved that let A be a square matrix. In the previous theorem, we proved that A plus A transpose is symmetric and A minus A transpose is skew symmetric, which means since for any matrix Ka, the whole transpose is K into A transpose, we can say that if A plus A transpose is symmetric, then half of A plus A transpose is also symmetric. If A minus A transpose is skew symmetric, then half of A minus A transpose is also skew symmetric. Therefore, combining these two, by adding half of A plus A transpose and half of A minus A transpose, we can see that plus half of A transpose minus half of A transpose will get cancelled, and we are left out with half of A plus half of A, which gives you A. In order to get A, we are dividing A plus A transpose and A minus A transpose by 2. Thus, we can conclude this theorem as any square matrix can be expressed as a sum of symmetric and skew symmetric matrix. With this, we conclude today's session. Thank you. ഒരു പ്രോബ്ലം ഉണ്ട് ഞാൻ വിട്ടു.